Hello, my name is Don Mercer, and the topic of this video presentation is mathematical modeling. Financial support for production of this series of video presentations was provided by the Széchenyi Society, the founders of the Hungarian programs at the University of Toronto. The Széchenyi Society's sponsorship is gratefully acknowledged. I would personally like to thank Dr. Leventi Diashadi, professional engineer and fellow of the International Academy of Food Science and Technology, who is a professor of the Department of Chemical Engineering and Applied Chemistry at the University of Toronto, for his considerable efforts in coordinating this project and making it all possible. The material in these video presentations is based on an e-book published in November 2014. Its title is An Introduction to the Dehydration and Drying of Fruits and Vegetables. It is available on the International Union of Food Science and Technology website. To access it, you can go to www.FIAFoST.org. We will begin with a brief introduction and follow this with some background information. Then we will look at the first steps involved in preparing a mathematical model of a drying process and then construct the actual model. We will then go to a general mathematical model and look at some other mathematical models as well. We'll finish up with some summary comments. In this video, we will look at the creation of a mathematical model from basic data gathered during a drying experiment. This builds on the information presented in the video conducting a drying run. For this example, we will use jalapeno peppers. Drying activities presented in this video were conducted using an Armfield tray dryer with air temperatures of 50 degrees Celsius and air velocities of 0.5 meters per second. And here we see the actual dryer. Air enters from the left-hand side of the photograph and is propelled by a fan that you can see there just inside the lattice work. The air blows across some heating coils and then progresses through the orange structure and leads to the upper right. Samples were placed on a wire mesh rack suspended inside the tray dryer. A linkage to an analytical balance allowed the weight of the sample to be followed during the drying process. And here you can see the wire mesh rack suspended from a knife edge that is in turn connected through this linkage to an analytical balance on the top of the dryer. I've also got a digital thermometer there for monitoring air temperatures, and the small stones that you see on the left were simply placed there to prevent that wire from becoming entangled with the linkage down to the rack inside the dryer. Please note that the drying kinetics and resultant mathematical models are highly dependent upon drying conditions. The nature of the material being dried and the configuration of the samples will also affect the drying kinetics. There may be noticeable differences in drying kinetics from one dryer to another as well. The first steps in preparing a mathematical model for a drying process include gathering replicate sets of drying data taken under identical conditions. Data will usually consist of sample weights at regular time intervals during the course of the drying runs. Knowing the initial wet basis moisture of the starting material for each run will allow you to calculate the weight of the water and the weight of the solids present at time t equals 0. For example, the initial moisture content of the jalapeno peppers in this study was 93.95%. If the initial moisture content of the jalapeno peppers is 93.95% on a wet basis, the solids content will be 6.05%. And this is simply 100% minus the percent water. The initial weight of the solids is going to be equal to the weight of the starting material times the percent solids as a decimal fraction. The weight of the solids at the start will remain constant throughout the entire drying run as long as there is no loss of solids. Occasionally, some solid particles may fall through the mesh on the drying rack or blow off the rack. However, this very seldom occurs if care is taken to avoid such situations and problems. Knowing the weight of solids throughout the run will enable you to calculate the weight of water present at each time interval. The weight of the water at time t will be equal to the weight of the sample at time t minus the weight of the solids, and this is a constant. Once you have the weight of the water and the weight of the solids at each time interval, the dry basis moisture can be calculated, and the dry basis moisture is defined as being the weight of the water divided by the weight of the dry solids. You can then plot the dry basis moisture versus time. You may want to base your work on the average dry basis moisture values from your 3 replicate runs. This is what has been done here. So here we see a plot of the dry basis moisture versus time for jalapeno peppers dried with 50 degrees Celsius air at a velocity of 0.5 meters per second. Using the built-in mathematical functions available in most computer spreadsheet programs, a trend line can be drawn through the data. The equation of the line, as well as its correlation coefficient, can be displayed. Correlation coefficients indicate how well the experimental data fit the computer-generated trend line. A perfect fit will have a correlation coefficient value of 1.000. The correlation coefficient is often designated as R squared. We will now take the plot of dry basis moisture versus time for the jalapeno peppers and find the equation of the trend line. There are various choices available, and these include linear and exponential functions. For a graph of this shape, the exponential curve works best. You may want to have the computer program determine the intercept value of the dry basis moisture for the trend line. That is, determine the dry basis moisture of the trend line where it intersects the vertical axis. If you are using the average of 3 dry basis moistures, you may want to specify the value of the intercept from the data that you have. The average initial dry basis moisture content is being used here to essentially force the intercept rather than letting the computer program determine it. This value is 15.53 grams of water per gram of dry solids. So here we see the plot of the dry basis moisture versus time for the jalapeno peppers with the trend line shown in red and its equation and R squared value shown here as the text in the red circle. We should also look up here at the top left and see where the intercept has been forced. It has been put into the computer program as being 15.53. So the trend line equation is y equals 15.53 times e to the minus 0.250 t, where y is the dry basis moisture at time t, and t is the time in hours. The value 0.250 is the rate constant for the drying process, and its units are in reciprocal hours, or hours to the minus 1. Let's take a look at this value. The larger the magnitude of the rate constant, the faster the water is being removed. The negative sign indicates the value of the dry basis moisture is decreasing with time in the dryer, which makes total sense since in the dryer we are removing water, so we expect to have a decrease in the dry basis moisture over time. The 15.53 value is the numerical value of the initial dry basis moisture of the jalapeno peppers that are being dried. The R-squared value, which is the correlation coefficient, has a value of 0.9978. This indicates that the mathematical equation fits the data extremely well, since the R-squared value is very close to being 1.000. Although this model is an extremely good prediction of the dry basis moisture value at any time t in the drying process, it has one very serious drawback. It is really only valid for jalapeno pepper samples having a dry basis moisture of 15.53 grams of water per gram of dry solids at the start. What we really need is a more universal or general mathematical model that can be applied over a range of initial moisture contents. Fortunately, this is not difficult to do. To construct a more general mathematical model, we will use what is known as a moisture ratio, and this is based on reduced moistures. Reduced moistures are defined as being the moisture content m sub t minus me divided by m naught minus me, where mt is the dry basis moisture at any time t, m naught or m sub 0 is the dry basis moisture at time t equals 0, and me is equal to the dry basis moisture at equilibrium, which occurs towards the end of the drying run. Since me, the dry basis moisture at equilibrium, is so very small, it can be safely eliminated or ignored in both the numerator and the denominator of this expression with very little effect on this ratio. The reduced moisture then becomes a ratio of the dry basis moisture at time t to the dry basis moisture at time t equals 0. So what we have now is the moisture ratio defined as m sub t divided by m naught. And this is a dimensionless quantity since it is a ratio of two dry basis moistures. What we ultimately want to do is get the equation of the trend line on a graph of moisture ratio versus time for the jalapeno peppers. We could just take the equation we have already generated and divide both sides by the initial dry basis moisture. We would then have m is equal to y divided by 15.53, and we will divide the 15.53 by 15.53, which gives us a value of 1, and multiply that by e raised to the minus 0.250t. So the final equation then becomes m is equal to e raised to the minus 0.250t. Since it is so easy to prepare graphs using spreadsheet programs, my personal preference is to calculate the moisture ratios for each time interval and plot them versus time. The initial value will always be 1.00, regardless of the actual starting dry basis moisture. Here we see the plot of the moisture ratio versus time for jalapeno peppers dried with the 50 degrees Celsius air and the air velocity of 0.5 meters per second. Note once again that the trend line is shown in red and we have its equation and the R-squared value for this. They're shown in the red oval. Take a look up in the top left-hand corner of the graph, and here you see that the intercept is 1.00. The R-squared value is equal to 0.9977, and the equation of this trend line is y equals e to the minus 0.250t. The trend line has the same basic equation as we showed previously for the dry basis moisture content versus the time relationship. And note that the R-squared value is almost exactly the same as for the dry basis moisture versus time graph. The two values differ only in the fourth decimal place due to round-off differences. The model for drying jalapeno peppers under these conditions is m equals e to the minus 0.250 t, where m is the moisture ratio m over m naught. The model can then be re-expressed as m over m naught is equal to e to the minus 0.250 t, which becomes m is equal to m naught times e to the minus 0.250 t, where m is the dry basis moisture at any time t. Let's apply the model to one or two times to show how it works. For time t equals 7 hours for a starting dry basis moisture content of 15.53 grams of water per gram of dry solids, we can calculate the value. This is actually going to be a point that we had on our graph. So we have m is equal to m naught times e to the minus 0.250 t, which is equal to 15.53 times e to the minus 0.250 times 7. Working this out, we find the value of m is equal to 2.70. Therefore, the moisture content at t equals 7 hours is going to be 2.70 grams of water per gram of dry solids. We can now go back to our original graph of the dry basis moisture versus time and see what the corresponding moisture was at 7.0 hours. So here we have a blow-up of that region of the graph. And we can draw a vertical line up from 7 hours and then scribe a horizontal line across to the vertical axis, and we see that this value is very close to the 2.70 grams of water per gram of dry solids that were predicted by the equation. We can also use the general model for a different starting moisture content and predict the dry basis moisture content at any time t. So we're going to use 7 hours once again, and we're going to have a starting dry basis moisture content of 11.5 grams of water per gram of dry solids, and this corresponds to 92% wet basis moisture. We can then substitute these values into the equation that we had, which is our general model, and we will get m is equal to 11.5 times e to the minus 0.250 times 7. Once again, we will work this out, and we find that the value of m is equal to 2.00. Therefore, the moisture content is 2.00 grams of water per gram of dry solids under these conditions. Some mathematical models fit the data better than others. This is reflected in the R-squared values, and if the fit isn't quite as good, you will have lower R-squared values. Let's take a look at the mathematical model obtained for drying Scotch bonnet peppers in the same dryer under the same conditions as the jalapeno peppers. Here we have the moisture ratio versus time for the drying of Scotch bonnet peppers. We get an equation, y is equal to e to the minus 0.162 t, and the R-squared value is 0.9875. That's not too bad, but when you look at the graph, you can see that the red line does not correspond entirely to the blue line for the data. The mathematical equation for the drying of Scotch bonnet peppers is m is equal to m naught times e to the minus 0.162 t. And we'll compare this to the equation for the drying of jalapeno peppers under the same drying conditions. And what we see here is the magnitude of the exponent is greater in the case of the jalapeno peppers than it is in the case of the Scotch bonnet peppers. This means that the jalapeno peppers will dry faster at the same conditions in the same dryer. Notice how the trend line deviates from the experimental data for the Scotch bonnet peppers in the middle region of the graph. This does not really make the equation unsuitable to model the drying process, however. We are interested in the time it takes to reduce the dry basis moisture to a very low value. Since the model fits very well for times after approximately 10 hours, it can be used as a predictive tool to gauge when the drying is nearing completion. One of the important uses of a mathematical drying model is predicting when a product is sufficiently dry to remove it from the dryer. To use the drying model for this, you need the actual starting moisture and the target final moisture. Both must be expressed on a dry basis. Recall that our sample of jalapeno peppers had an initial moisture content of 93.95% on a wet basis. For example purposes, we'll use a target moisture content of 10% on a wet basis for the final product. These must both be converted to a dry basis. So 93.95% wet basis moisture will equal 15.53 grams of water per gram of dry solids, and 10% wet basis moisture will equal 0.111 grams of water per gram of dry solids. So here's our model. We need to solve for T, and this will give us the time required to dry the product from its given initial moisture to its final target moisture. Rearranging things, we can take the equation m is equal to m naught times e to the minus 0.250 t and rewrite it as m over m naught is equal to e to the minus 0.250 t. We can then rewrite this as being minus 0.250 t is equal to the ln of m over m naught. Getting rid of the negative sign, we can write 0.250 t is equal to the ln of m naught over m. And that will be equal to the ln of 15.53 divided by 0.111, where both of these values have units of grams of water per gram of dry solids. That in turn equals the ln of 139.9, and when we solve for that, it gives us 4.94. So 0.250 t is equal to 4.94, which means that t is equal to 19.8, and that has the units of hours. Therefore, it would take almost 20 hours to dry these jalapeno peppers to the desired final moisture content. And this is a rather long process. So in summary, in this video we have shown how to construct a mathematical model that can be used to predict the dry basis moisture content of a material at various times. Such mathematical models are quite valuable for use in industrial applications. They are useful for calculating drying times of various batches of materials. And it must be remembered that the mathematical model will vary with the type of dryer and the drying conditions. Different materials will have different drying properties. Sample configurations will also have an impact on the drying kinetics, and by this I mean typically the thickness of the slices and any irregularities that might be present in the material itself. Thank you very much.